Good morning. I will present you the joint effort. I will present you the joint effort of the Donors Institute. I will present you the joint effort of the Donors Institute, and actually several universities in the Netherlands have been involved in our approaches. So actually, as already explained by Walter Snyder, it is a very pioneering quest to segment the brain, and we tried several methods because we didn't know where to start. So we had a very simple method. It's called geometric k-means, and we used this as our baseline. And actually, we were never able to surpass this baseline. So I will give you an introduction to 3 of our methods, and which are basically 2 structural methods and 1 fMRI time series-based method. So the geometric k-means method is based on the locality of the gray matter voxels. And what you typically get is some nice patches across the whole brain, which are equally sized. Also, you can see that the patches are quite symmetric, and they are aligned with the salsa in the brain. So actually, doing this, we for brain 0, we got a score of 30% or higher using 260 patches per hemisphere. So this was our baseline, like to see how good our methods actually are. Well, it is important to note that 30% scoring means actually 65% cluster overlap. So that's actually a pretty good overlap with the clusters. So don't get distracted by the low percentage scores. So at the Donors, we're actually interested in building networks, which are looking like this from the Hachmann paper. And the reason why we want to look at those is we are interested, how does a network change when we have significant dropout by a lesion, for instance, stroke by a patient. And in order to come to good conclusions, it is for us important to have a really reliable network. As already Hartmann pointed out, this is just 0.01 beta version of the brain network. And it is our goal to get the best possible network which is out there. And in order to get a good network, we believe that it is important to know the strengths of the connections between the nodes in the network, and also it is important to define what is actually a node inside the network. So the approach by Hachmann used 1000 ROIs. So, but what is a good node? So then we take a step back and to see where graph clustering, graph theory actually came from, and then we see that Euler, he used nodes to represent landmasses in the city of Königsberg, and he used edges to represent like bridges to solve the question. And I want to note here that it's critical to represent the landmasses with the nodes in a proper way, because if we, for instance, like use this landmass in the middle and the one at the right together as one node, then we get a completely different network, and the interpretation will be very different from what should be done, and we cannot solve the issue. So the idea here, our approach in the Donors is, well, our nodes are actually the visual areas in the brain, which are like outlined also by the competition, such as V1, V2, and V3. But already here we have like a skeptical remark. We think, for instance, that V1 can be separated into 2 regions because the bridges from the top side of the V1 area here are like going this way to the top, and the bridges from the lower V1 go like below. So we have to wonder whether we want to represent V1 as a single node, or whether we want to like represent V1 with 2 nodes. So this is a typical brain, represented as a full graphical representation. Now, please note that the edges are well, not weighted, so it's maybe a little confusing. But so the question is, how do we get here? This already is a very reduced version of the brain. Actually, it's just containing 1000 nodes. So So we tried something quite radical. We tried a voxel-based approach. And we did probabilistic stratigraphy from every seed voxel inside the gray matter mask. And there are around 70,000 voxels inside the gray matter. And we start seeding like from any voxel within the brain and look where these seeds take us. And we seed around 1,000 times per voxel. And we get a huge matrix from 74,000 by 74,000. This matrix you probably have seen already quite often. People usually use the AAL template, but yeah, the more higher the resolution, the better. So how does our matrix actually look like? Now I want you to visualize the whole room painted with this graph and beyond, just also the hallway. Then you get a good picture of what our connectome actually is. So it is a very high complex graph. And the question is, how do we make sense of it? How can we get something useful out of it? And the way we did is we used random walks, which is a quite simple solution actually. And, or we can also call it flow simulation. So we randomly walk through a graph structure and we identify edges which are not visited very often. For instance, here below. And then we iteratively prune those edges which have not been visited a lot. And we slowly get to see small network structure or cluster structure emerging. Doing that on our matrix, we get about this kind of clustering, and across brains we get 2,000, around 2,000 clusters per brain. So actually this is quite consistent. So brain 0 had 2,000 clusters, brain 1 had 2,000 clusters, and brain 3 had 2,000 clusters, even though the voxels numbers were quite different. And so we think this is a very promising approach. This is an interhemispheric network cluster, which is quite rare, which yeah, it happens quite rarely. This means that there's a strong connectivity between the left and the right hemisphere and the temporal lobe. Well, my colleague will introduce you to what we think is also a very promising way to approach this problem, and it's based on fMRI time series. And I hope you